In this lesson, we're going to talk about how you can solve exponential equations and logarithmic equations. So loaded on the front end of these notes, they have been revised from the ones that you may have received to include some explanations and some examples that are worked out and problem-solving strategies on how to solve these equations. So you may want to pause and read this section or look at the blank revised notes on the portal to read this additional information, but we will work the example problems at the end of these notes. So at the beginning of the notes, you will see that you have some information that will allow you to better determine how to solve exponential equations. So for example, you see this exponential equation. If there is a way to rewrite each side of the equation with the same base, then all you have to do is equate the exponents and solve for the unknown. So this first page is going to tell you if you can rewrite each of the equations with the same base on either side of the equation of the equal sign, then there's a method to easily solve exponential equations. Now on the next page, you'll see an example. Here you have written that original example where each side of the equation is a power of the base 2. So you can just equate the exponents. Now, what happens if you can't write each side of the equation with the same base? So in other words, you're solving exponential equations with different bases. Well, you're going to have to introduce some logarithms. So you may want to take the log of both sides. Now, it's easy to take the common log or the natural log of each side, but knowing your properties of logarithms, you may want to go ahead and use the base of one of the sides of the equations. And for example, here, instead of taking log base 10, a common log of both sides, perhaps you might want to take log base 8 of each side, which would allow you to easily simplify the left-hand equation of side of the equation. So there's different ways to solve exponential equations by introducing logarithms, taking the logarithm of each side of the equation when you cannot represent each side of the equation with the same base. Again, you can do the common log of each side, the natural log of each side, or cleverly choose a logarithm of the base of one of the sides of the equations. Again, different ways to solve these problems, but if you're going to log both sides, the base of the log that you are taking of each side must be the same. So here are some examples. And then there is another example. Again, you need to know your properties of logarithms to be able to easily solve these equations. So in example 2 here, you see that you can rewrite each of the sides of the equation with the same base. In this case, I don't see that I can do that. However, if I take the natural log of both sides, I can use my properties of exponents and what I know about natural logs to simplify this easily. Now, you can always get an exact solution where you may have ln or log of a base in your answer, or you can actually, if it's a common log or a natural log, put that into your calculator and get an approximate solution. So you will have to be able to take an equation, use the proper method to solve it, and be able to give an exact solution or an approximation, an approximate solution. So these are two different things at times. Again, another example that will allow you to see which is the best method to solve these exponential equations. Now, if you are solving a logarithmic equation, meaning you already have a log, whether it be a natural log or a common log, if you already have a logarithm in the equation, well, then you don't take the log of both sides. Instead, you make each side the power of a base. And cleverly choosing the base that you want to raise each side to, you want to think about what the base of the logarithm is. So this is when you want to, instead of taking the log of each side, you may want to exponentiate each side, meaning introduce a base where each of these sides of the equation are the exponents to that base. And again, you have to choose the same base to exponentiate both sides, each side of the equation. So these are just some examples that will allow you to see the different steps of how we're solving them. So again, you may want to pause, read over these examples, try the examples on your own before you look at the steps to see if they make sense. Now we're going to go ahead and do some practice problems. Now, just to remind you, if you are just solving a simple linear equation, remember you want to isolate the variable. We are ultimately trying to find the value of the variable. If there is a value or values of x in these instances that make these statements true. So if I were to try to isolate the variable in the first example, well, you would subtract 10 from both sides, giving you 3x equals -6, and then you would divide each side by 3, and you would get the solution to be x equal -2. Now this is a very simple equation, a simple linear equation, one variable, but the idea is still the same. We want to isolate the variable. So here in the next example, you are being asked to find the exact solution as well as the approximate solution. So we're going to still go through the same process. We notice we want to find the value of x. So we're going to start moving things away from that side of the equation to isolate the variable. So perhaps your first step here would be to add 600 to both sides, to each side. So that would give you 400 times e to the power of 0005x equals 1600. Now, we're still trying to isolate the x, so perhaps the next step would be to divide each side by 400. If you were to divide each side by 400, well, you'd be left with e to the 0.0005x equal 4. Now, the unknown x, the value of x that we're trying to find, is in the exponent. Now, I see a base of e on the left-hand side of the equation. So I'm trying to think, what can I do to the left-hand side of the equation to be able to maybe use a rule of logarithms to be able to get that x out of the exponent? Well, if I take the natural log of each side, so I'm going to ln each side. If I take the natural log of the left-hand side, I have the natural log base e of e to this power. This is going to simplify to just 0.0005x using your properties of logarithms. And that is going to equal the natural log of 4. Now, I'm still trying to solve for x. So perhaps the next step would be to divide each side by 0.005x. Oh, not x, just 0.005, sorry. And divide the right-hand side by 0.0005. Now, for the exact solution, I have x equals the natural log, ln of 4, over 0.005. That is an exact solution. If I want to find an approximation of x, well, I can evaluate the natural log of 4, so I'd go into my calculator and I'd select ln of 4, and then divide that number by 0.0005, and I would be able to get an approximation. And an approximation, if you were to put that into your calculator, would be 2772.589. So try to put that in your calculator. Put the natural log of 4 divided by 0.0005, and you should be able to get that approximation. So you have an exact solution and you have an approximate solution. You should be able to do each. Now, looking at the next example, again, I want to find the exact as well as the approximate value of x. I see that x that I'm trying to find is in the argument of a logarithmic expression. So now we need to figure out what we're going to do first. Well, just like a regular linear equation, I'd start stripping things away from the term that involves the unknown value x. So I'm adding 3 to both sides. That's going to give me log base 6 of the argument 4x minus 1, that's the input, equals 3. Now, I see a log base 6 of an argument. How can I possibly get rid of that logarithmic part of the left-hand side of the equation? Well, I can exponentiate. In other words, I'm going to introduce a base and make each of these the exponent to some base. Now, what base am I going to choose? Well, I see the base of the logarithm is 6. So now I'm going to introduce a base 6 and make this the exponent of each side. Now, using my properties of logarithms, I see 6 raised to the log base 6. That goes away, remember, leaving me just 4x minus 1 on the left-hand side, equaling 6 cubed. This turns into a nice simple linear equation we can solve. 4x minus 1 equals, well, what is 6 cubed? 6 times 6 times 6 is 216. Next step would be to add 1 to each side, giving me 4x equals 217. And then I divide each side by 4, which would allow me to get the exact solution. X equals 217 divided by 4. And the approximate solution, if I were to perform the division, would be 54.25. Again, I can get an exact and approximate solution. Sometimes they're the same thing. If this had divided evenly, which, well, look, I see it does, they're the same thing. Now, in the next example, I have an exponential equation. What can I do to each side? I see the variable x is in the exponent. There is no way to get each of the sides of this equation to be the same base. So I need to take the log of both sides. Well, you could take log base 7 of each side. You could take log base 3 of each side. You could take the natural log of each side, or I could take the common log of both sides. And I'm going to go ahead and take the log of both sides. And I'm going to take the common log. So while I have 7 to the 2x plus 1 equals 3 to the x plus 3, I'm going to take the log, the common log of each side. Now, using my property of exponents, in particular using the power rule, I can now move these exponents in front of the logarithmic expression. So that would give me 2x plus 1 times the log of 7 equals x plus 3 times the log of 3. Now, at that point, I would want to distribute. So I'm going to go ahead and distribute. And what am I going to distribute? Well, I'm going to distribute this log to each of these terms. And that's going to give me 2x times the log of 7 plus the log of 7. And that's going to equal x times the log of 3 plus 3 times the log of 3. Now, I want to try to get my logarithms on the same side where I can easily simplify. So everything that has an x, let's say, I want to take to the left-hand side. So what has an x term? This has an x term. This has an x term. So perhaps I want to subtract that x log of 3 from each side. Oh, I forgot the 3. My apologies. So now this is gone. So on the left-hand side, I have 2x times the log of 7 minus x times the log of 3. And I'm going to go ahead and subtract that log of 7. Let me get a different color. From each side. So my right-hand side would now be 3 log of 3 minus log of 7. Now, each of the terms on the left-hand side have an x. So perhaps you want to factor out an x. So I'm going to factor the left-hand side. I'm going to factor out an x, which would leave me 2 times log of 7 minus log of 3. And that's going to equal my right-hand side. Now remember, I'm trying to solve for x. So how can I isolate the x? Well, I'm going to divide each side by, this is just a number. If I were to put this in the calculator and evaluate this and subtract this, this is technically a number. So I can divide both sides by that. So all I have left on the left-hand side is x. And on the right-hand side, I have 3 times log of 3 minus log of 7 over 2 times log of 7 minus log of 3. Now, this turns out to be the exact solution. It has logarithmic expressions in it. If I wanted to get an approximate solution, I would actually type in my calculator 3 times the log of 3 minus the log of 7, get that number, divide it by 2 times the log of 7 minus the log of 3. So go ahead and try that, and let's see if you can get the approximate solution to be x equals 0.483. That would be your approximate solution. Now, the next example, I'm looking at this. Oh, hopefully you recognize what's happening here. There's a nice little shortcut. If you remember, I can look at this and go, ooh, I see a trinomial on the left-hand side. Kind of want to factor it, but maybe it's difficult to factor as is. So I can go ahead and introduce a variable u and let u equal e to the 2x. So therefore, u squared would equal e to the 2x squared, which is e to the 4x. So after introducing this variable u, I can rewrite my original equation as in terms of u. So u squared minus 3u minus 18 equals 0. That's a beautiful quadratic trinomial on the left-hand side of this equation that I can easily factor as the product of two binomials, u plus 3 and u minus 6. Now, using the zero product property, I can take each of those factors and set them equal to 0 and solve for u. And then I can recall what u equals and replace that u with what we said it equals, which was e to the 2x. And then I'd have to say, all right, I don't like those variables in the exponent. How am I going to solve for x? Well, I see the base of each side, of each left-hand side, is e. So I can take the natural log of each side and then use the property of logarithms to simplify the left-hand side as 2x equals ln of 3 and 2x equals ln of 6. Ooh, this is a negative 3. My apologies. This is a negative 3. Now, that right there should be concerning to you, because if we recall what the parent logarithmic function looks like for any base, I know that I have a vertical asymptote at x equals 0. So I can't have an input to a parent logarithmic function that is negative. The logarithmic function only exists in the first and the fourth quadrant. There is nothing going over to the left of the y-axis. So right here, I know I can't have that. I can't have a negative input to a logarithmic function. So I know automatically that that is not going to be valid. That is undefined. However, on the left-hand side, I can go ahead and divide each side by 2 and get x equals the natural log of 6 divided by 2. Again, this would be your exact solution. And if I wanted to find an approximate solution, I would go ahead and take the natural log of 6 and divide it by 2, and you should be able to get 0.896 as your approximate solution. 3 significant digits is sufficient unless otherwise stated. One more example. Here I have a logarithmic equation. Now, I see that I have the difference of logs on each side. So this difference of logs, hopefully you remember that I can represent the difference of logs with the same base, and in this case they're both natural logs, so the base is e, as the quotient, the log of a quotient. So using the quotient rule for logarithms, I can rewrite this difference of two logs as the natural log of the quotient of each of those arguments. And I can do that for the left side as well as the right side. Now, at this point, I see I have natural logs of either side. How am I going to get rid of the logarithmic part of this? Well, I can exponentiate both sides. So exponentiate both sides. And what that means is I'm going to take each side of these equations, of this equation, and I'm going to make each side the exponent to a base e. So I'm exponentiating both sides. I'm introducing the base e and making each side of the equation exponents. Now, knowing that ln is log base e, I have a beautiful property that allows me to simplify the left-hand side to be x minus 5 over x plus 4, and that's going to equal x minus 1 over x plus 2. And I can cross multiply. So I can multiply across the equality. So I have x minus 5 times x plus 2, and that's going to equal x plus 4 times x minus 1. Now, I just have the product of binomials on either side of the equation, so I'm just going to FOIL each side. So the left-hand side is going to give me x squared. I'll show all my steps. And the right side first, outer, oops, inner, last. And then I'm going to combine like terms. So x squared minus 3x minus 10 equals x squared plus 3x minus 4. Now I'm solving for x. I see that I have an x squared on either side, so I can subtract x squared from each side, and they go away. And then I have minus 3x minus 10 equals 3x minus 4. So perhaps let's get all our x terms on one side of the equation. So that's going to give me negative 10 equals 6x minus 4. And then I'm going to add 4 to both sides, giving me negative 6 equals 6x. My last step in solving for x would be to divide each side by 6. So then that gives me x equals negative 1. Now that's great. Algebraically, we found the value of x. But we have to check to see if this is an extraneous solution, remember? So if I take this and I come back up here and I say, what happens if I substitute in negative 1 into this first x? Well, that's going to give me the natural log of negative 6. So I recall again that the input to a logarithmic parent function, the argument, the input cannot be negative. So I know that this is an extraneous solution. So as a result, there is no solution to this equation. I cannot have an input that is negative. So as soon as you get a negative input to a parent logarithmic function, it is undefined. And you're done.